Okay, variable and distributed forces. I'm just going to go over a couple of these. 19. When you plot the force exerted on a particle, remember what's a particle, as a function of the particle's position, what feature of the graph represents the work done on the particle? So if we've got force, right, remember these are always external forces, but I mean if you've got a particle, then all the particle's just a little dot, right? Okay, and you've got the position. Okay, so this could be anything. So we're now looking at variable forces, so this force could be constant, it could be like linear like that, or it could be increasing. Okay, this force is changing. It could be constant or it could be changing as the particle displaces. Okay, so when you plot this, what feature of this graph represents the work done? So remember, the work done is simply the integral of the force times displacement, f dx. Okay, so the integral, remember the integral is simply the area under the curve. So for this one, you would calculate then the area under that curve, and that is your work done. For that red one, you would calculate the area. For the black one, area under the curve. Okay, so area under the curve represents the work done. Okay, 21. You use equations 927 and equation 928, you can go look at that, to calculate the thermal energy dissipated by friction. I think 928 looks like this. Delta E thermal equals the friction force between the surface and SB. I've written down B here, so it's just between the surface and the crate. I got this from the textbook. I don't know why there's a B there, if somebody can remind me. Anyways, it's the friction force between the crate and the floor, okay, multiplied by d path, which is the total distance. Remember, the idea is still the same as a delta x, okay, but we're looking at the total path that this guy travels. Okay, so it is the change in the thermal energy is equal to the friction force multiplied by the path that it travels. Could this thermal energy be called the work done on the crate by the frictional force? Well, we've seen this many times. If you've got the crate and the floor, there's a friction force, but remember the friction force, first of all, it's distributed over that whole surface, so it's not possible to find a single point of application that the friction force is being applied at. So we can't calculate that, the delta x of that point. And secondly, both surfaces, the crate and the floor, are, let's make this red, are heating up. Okay, they're both heating up. So we don't know how much thermal energy has gone into the crate and how much thermal energy has gone into the floor. Okay, so it's difficult. Remember, work is the change in energy of your system. So now if we make the crate our system, if we can't measure that amount of thermal or the force that's being applied is causing this to heat up and that to heat up. So it's difficult to measure that energy, so we can't say that it's work done. Furthermore, this force is not necessarily external to the system because it's a friction force. Okay? So it cannot be called the work done on the crate by the friction force. Okay? Alright.